In recent times, generative design has become a bit of a hot topic. As computer technology has advanced, it's become more accessible, and as manufacturing has become more flexible with the rise of additive manufacturing methods like 3D printing, generative design has also become more useful. It's quite likely that with further advances in these areas, generative design will become an important tool in the future of engineering. So what exactly is it? In simple terms, it's the process of allowing the computer to do the design work for us. The idea is that we tell the computer what we want to achieve, and through an iterative process, the computer can generate a range of designs that fulfill our requirements. The resulting designs are often described as organic, with shapes that have many complex structures and curves that would be a challenge to model manually. In saying that, we do have the ability to specify the manufacturing process we want to use to make the design, and this will have an impact on the results we get. We can get outcomes that can be made from additive manufacturing, milling, 2D cutting, and even casting, however not from general fabrication techniques. Generative design is realistically still in its infancy, so the results can be somewhat limited when it comes to generating a complete design for a part that can actually be produced. For example, think about a tube chassis for a race car. We could use generative design functionality to create a design to fit our requirements. But the result is not going to be something we can manufacture accurately from tubing, and there's no chance we are 3D printing or machining something to that scale. With that said, the results still might be useful as inspiration and guidelines to work off to give us a general idea of what geometry might be ideal. There are a few other benefits that generative design presents other than saving time. The first being that the program works to create an optimal design for us based on our requirements. For example, if we prioritize weight, we'll get the lightest part that achieves the required strength. Of course, that won't give us the actual most optimal design, as this is an iterative process, but after a relatively short period of time, we can get something that's close to optimal. On top of this, subconscious constraints from experience aren't a factor. By this I mean it's natural for humans to tend towards certain solutions based on previous experience, causing us to overlook other possibilities. Computer software doesn't have this problem, so some of the results might be unexpected and inspirational. Much like simulation, generative design is an extension in Fusion 360, meaning that there's costs associated with its use. The current cost is 11 tokens per study, which ends up being around $30 US. This can add up quick, so if you're going to use it, you really want to make sure everything is correct to avoid having to run multiple studies to fix mistakes. The process in Fusion 360 is also comparable to the simulation study process. So let's have a look at doing that now. Again, remember that this is more of a 30,000 foot view, just to give you an idea of how it all works in practice, not a detailed how-to guide. For an example, let's look at the rear mount for the Hollinger sequential gearbox in the HPA Toyota 86 race car, as this is a fairly simple part of the system where it's easy to understand the loads and constraints. The part has already been designed and fabricated and has served its purpose for multiple race seasons, so we know it's a proven design. Let's use the generative design process to explore alternative solutions that use the same mounting locations for the hardware to the chassis, as well as the nolethane bushing between the mount and the transmission. I've modelled the chassis fixture points and a simplified version of the rear of the transmission, including the bushing in Fusion 360. Getting started, when we navigate to our generative design workspace for the first time, we get a pop-up window giving us the options of structural component or fluid path. For our transmission mount, we're going to want to choose structural component, but we can also use generative design to model fluid paths, which could be used for various automotive applications. Once in our generative design workspace, we can see our toolbar is fairly similar to the simulation workspace, and we also work from left to right along it. At the far left, we have this guide icon. This brings up the learning panel, which can be used to help us through the process. Next on the toolbar, we have the Study tab, which is where we can create a new study. We already have a study which we can see in our browser, but we could use this icon to add another study if we wanted to use different setups and get different results. For example, we could use the same chassis mounting points but for a different transmission with an alternative mount. Under the Study tab, we can also access our study settings. This gives us a pretty simple option for resolution between fine and coarse. Just like our meshing for FEA, finer resolution does give us better results, but more coarse will mean faster computing time. Let's just leave this as is for our example. With the basic settings out of the way, we can get into actually setting up our model for the generative design study. Starting with the Edit Model tool, we can think of this like the Edit in Place function when working with external components and assemblies. This allows us to edit our model without changing back to the design workspace. Generative design studies actually require multiple bodies. More specifically, and looking ahead in our toolbar for a moment, these bodies are used for preserve and obstacle geometries, which are the key geometries that our study will work from. As the names imply, the preserved geometry is incorporated into the resulting design and the bodies are not changed. The obstacle geometry, on the other hand, will be areas that are avoided by the resulting design. With these requirements in mind, we'll select the Edit Model function to make some suitable bodies for preserve and obstacle geometries. Starting with preserve geometries, we want to think about parts of our model that we want to be included in the final design. In our case, we want to preserve some material around the bushing to ensure it's encapsulated in the final design. Just a note here, surface bodies can't be used for preserve or obstacle geometries. These must be solid bodies. We can model a simple cylindrical sleeve 1 mm thick around the bushing for this purpose using an extrude or revolve. We should also preserve geometry around the chassis mount holes to ensure we can actually bolt the solution in place. Let's make a 3 mm thick plate on each side that the hardware can fix through. We'll use the project, offset and line sketch tools and then a simple extrude to do this, making sure these are new bodies so we can use them separately from existing geometry. We'll also be able to use these in a few moments for our structural constraints. While we're in the Edit function, let's also create some bodies for our obstacle geometries. The important areas for this will be the spaces inside each chassis mount hole that the hardware needs to go through. Luckily, we have this connector obstacle in our toolbar specifically for this. So let's select it and then click the inner circular edges of the plates we just created for the start of the shaft. For the end of the shaft, we can just select the corresponding edge on the back of the mounting point. Then we can set the bolt head diameter and length of the connectors based on the hardware we intend to use, which will be 13 and 8 mm in this case. We also have the tool clearance preference. Using this will allow easy access to the hardware. Now we have 4 more bodies for the connectors that can be used for obstacle geometry. So let's finish editing the model, select the Preserve Geometry function, and select the solid bodies for the 2 plates and the sleeve around the bushing. These bodies will turn green. Then the same idea for the obstacle geometry, selecting the solid bodies for the connectors, chassis mounts, and the rear of the transmission, which will turn red. Let's also use the Obstacle Offset tool to set a clearance distance of 2 mm around the connector obstacles and 5 mm around the transmission, just to make sure that there's no chance of interference with the result. Now we can move on to the design conditions. We'll start by adding 2 structural constraints. Naturally, these need to be fixed constraints at each chassis mounting point. We need to hide the connector bodies and select the internal cylindrical faces of the plates to apply these. After this, we can add our structural load, which is the key part of this process that needs a bit of extra thought. This gearbox weighs about 35 kgs, but it's also connected to the engine, which is supported by the mounts, as well as the drive shaft and various other fittings. So it's quite tricky to put an actual figure on how much weight is supported by this mount. On top of this, The car pulls between 1.5 and 2 Gs when cornering and braking, and the mount is subject to significant amounts of heat and vibration. No torque can be transmitted into the mount though, since the bushing is a pin joint. In the interest of simplicity for this example, we'll say the mount can see up to a 1000 Newton downward load and also 1000 Newton load to each side, assuming that all other loading is supported through the engine mounts. Selecting structural loads with the type set to bearing load, we can set this up on the inner face of the cylindrical preserved geometry around the bearing. A bearing load represents the load distribution in the contact areas between shafts and bearings or bushings. Essentially, compressive force on half the cylinder with the intensity focused towards the midpoint. Next, we set the direction type as angle and apply a 1000 Newton force downwards. We may need to toggle the flip direction button to get this right. After this, we can right-click to clone the load case twice, reducing the downward load to 500 Newton for each clone and also adding a 1000 Newton force to the left on one clone and to the right on the other. The 1000 Newton downward load case represents the load through the mount as the car moves through a harsh bump. The other load cases represent the load through a corner but also retain some degree of downward load. The resulting design from the generative study must satisfy the requirements of each load case individually, but not all at once. This is because if both sideways loads were applied at once, they'd effectively cancel each other out. The other load we see in our browser for each load case is labelled gravity, and this is just the force on the component from its own weight, which is insignificant for this example. And with that, we've completed the setup for the geometry and the load case. Next along the toolbar is specifying the design criteria. Selecting the objectives icon, we have some more simple options that are going to have a big impact on our result. The big question here is, do we want to minimize mass or maximize stiffness? If we want to minimize mass, we can choose a suitable safety factor we want to use. For example, since our first load case has a 1000 Newton force, a safety factor of 2 means that the resulting design could handle up to a 2000 Newton force without failing. If we want to maximize stiffness, we can still specify a safety factor, but also a target mass. Although stiffness would be important for our design, for this example, we'll choose to minimize mass and set the safety factor to 1.5, which seems suitable for this example because our load values are likely already overestimated. The other setting under the design criteria is manufacturing. By selecting this, we get options of what manufacturing method we want to include in our study. In other words, what are the possible options we have for producing this part and what methods do we want to consider? We'll be given a range of results for all the selected methods. At the top of the list, we have the option to include cost estimation, and then underneath we find a range of different methods. Hovering over each will give you some more information. In some cases, we need to consider the orientation or tool direction. For example, for 3-axis milling of our concept, the tool direction should be the negative X direction. Let's just select unrestricted, additive, and 5-axis milling for our study, leaving all the other settings as default. The final field we need to look at is material. This isn't necessarily the physical material that we have specified for the design concept. Like the manufacturing setting, we can choose to include a range of options that we might want to consider and will be given results for each of these materials. We can include materials by dragging them up from the library section into the In This Study section. For this study, let's use aluminium from the additive material library as well as aluminium from the standard material library. Now we're all set to generate some results. Much like the simulation studies, we can use the pre-check function to make sure we have all our bases covered. We can also use the previewer tool before we generate to get an idea of the general shape of the results. Note, this previewer tool will continuously change as it goes through its own iterative process. To stop it, we just click the previewer icon again. I've personally found the previewer function to be quite temperamental and often not work, even though the final results generate without issues. However, with the cost of running these studies, it's definitely worth using the pre-check and previewer tools to make sure we're going to get useful results. If the results from the previewer show some clear issues, additional obstacle or preserved geometries may be needed. Alternatively, an existing modelled body can be assigned as a starting shape, which is coloured yellow. This acts as an initial shape for the generated outcome. Naturally, this is taking away from the flexibility of the generative design study, but allows us to tailor the general form of the results towards what we want. We won't need a starting shape for our example, so we can bypass this step. Finally, we can now select Generate, and we'll get a pop-up window explaining the cost of the study, how many tokens or cloud credits we have, and how many will be remaining after the study. Depending on the power of your computer, this will likely take a while to complete the study. After it's complete, we're automatically taken into the Explore workspace where we can see all the results from the study. We can use the tools down the left-hand side of the screen to filter the results, and if we double-click on any of the outcomes, we can view it in more detail and also export it as a new design under the Create tab. After this, we can open the design and work with it like any other. Notice the processes in the timeline that build the design, including the preserves and obstacles. There's also an organic feature, which creates a complex outer shell and then a boundary fill which forms the solid body. From here, we could export an STL file to 3D print the part, a step file to get the part machined, or just use it as guidance to create a new model that can more easily be created with other manufacturing methods. Now that we've got the outcome from our generative design study, I want to quickly discuss the automated modeling and our solid modeling design toolbar, which is a very recent addition to Fusion 360. This is essentially a simplified version of generative design, and now that we've had a good look at the process, the differences between the two will be easier to understand. Automated modeling doesn't allow us to specify the loads that our design needs to withstand or anything to do with the manufacturing process. However, unlike generative design, automated modeling is free. Let's have a quick look by selecting the automated modeling icon in the toolbar for our same gearbox mount model. Naturally, the process here is a lot more straightforward than with generative design, but the general idea is the same. First, we select the faces to connect, which is basically our preserved geometry. We can select the outer faces of the chassis mount points, as well as the outer face of the sleeve around the bushing, which will be highlighted blue. Lastly, we select the bodies to avoid, which is just like our obstacle geometry. For this, we'll select the bushing, chassis mounts, and the rear of the gearbox body, which will turn red. After this, we just hit Generate Shapes, and we're given a range of solutions in the Alternatives field. The number of these can vary depending on our model and inputs. Clicking each one will show a preview in our model space. If we select one and hit OK, this will create a new body or component in our workspace, depending on what we choose for the operation preference. The resulting organic features in our timeline are similar to the generative design process. Now, this model would need some more development and refinement before it's something we would want to manufacture. Also, although the design alternative given is comparable to our outcome from generative design in this case, in other cases it may be completely different. This design is really just an alternative way of connecting the faces and avoiding the bodies we selected without considering any loading, meaning it's a helpful way to explore alternative design options, but these designs still need to be tested in the simulation workspace to be developed to a point of the generative design outcome. We've covered a lot in this module, so let's recap the key points. Generative design is the process of our computer generating a design for us based on a range of inputs and specifications that we define. In Fusion 360, we need to set up the design space, including the geometry we want to keep in the areas we want to avoid, being the preserve and obstacle geometries. We can also use a model for the starting shape to have more control over the form of the resulting designs. Next, we set up the loads and constraints to outline the load case, much like the simulation process. Finally, we define the objectives, either to minimize mass or maximize stiffness, as well as choosing which manufacturing methods and which materials we want to consider in the study. Just before generating the outcomes, it's helpful to run a pre-check and use the previewer tool to make sure everything is set up how we intended to avoid wasting the associated costs. After generating the outcomes, we can export them and work with them like any other design, either using it as a guideline to develop other concepts or work towards manufacturing. That was one of nearly 60 modules taken from the HPA Automotive CAD and 3D modeling course. Often, the parts you need just aren't available for your particular application off the shelf, but that doesn't mean you have to give up and compromise with substandard bolt-ons. You can learn to design your own to your exact requirements and with your own personal touches and style added. So if you want to take your project vehicle to the next level by learning how to design your own lighter, stronger, and better fitting parts from scratch, this course is a great place to start. You'll learn everything you need to know in order to accurately design custom parts and equipment for your car. That means an understanding of design fundamentals, solid and sheet metal modeling, assemblies, 3D scanning and printing, and post-production in order to get your part ready for manufacture. If you're someone who's tired of the lack of availability of parts for your application, or you just think you could design what's out there better, then the HPA Automotive CAD and 3D modeling course is going to be the perfect way to pick up some new skills, save money, and take your builds to the next level. For more information and to purchase this course, click the link to enroll now.